The next speaker, I'm pleased to welcome and introduce our second speaker, Kaustubh Mhatre, who is a PhD student in the Computer Engineering Department at Arizona State University in Tempe. His research interests are in the field of domain-specific acceleration for machine and deep learning, focusing on heterogeneous computing architectures. He will present on performance analysis of GEMM workloads on the AMD Versal platform.
Hello everyone, I'm Kaustubh Mhatre, a PhD student advised by Professor Raman Arora at Advent Lab at ASU. So today I'm going to present our work on performance analysis of GEMM workloads on AMD Versal. A special thanks to HACC UIUC for providing us with the resources for this work. So before jumping into the analysis, I would like to provide some motivation for our work. We know that GEM is the heart of most of the deep learning applications, as due to the advent of transformer, most of the applications in the deep learning domain are GEM. And there has been various efforts to analyze GEM on CPU and GPU as they are very well-known hardware, but there is not much efforts done to see how GEM operates on, say, heterogeneous hardwares like Versal, AMD Versal. So my work extensively analyzes GEM workloads on different size and shape on AMD accelerator, AMD Versal specifically, which is a heterogeneous accelerator with AI engines and the programmable logic. So in the upcoming slides, we will share our experience using AMD Versal and go over our analysis. So before starting the analysis, I would like to give a brief intro of the hardware. So AMD Versal is a heterogeneous architecture that consists of AI engines and programmable logic. We've specifically in our research used VCK 5000 and for all the analysis. So it also has the communication aspects of VCK 5000 include like the PL/IO interface, the AI to AI communication schemes, which we'll talk later, and the DRAM to the PL bandwidth. So before starting with the experiments, I'll give an overview of matrix multiplication and how we have used the notation of M, K, and N throughout our presentation. So a typical matrix multiplication has a matrix A, which is M by K, and then a matrix B, which is K by N, resulting into a matrix C, that is M cross N. So this is of the form MKNN, which we have used for the notation for all our workloads throughout the presentation. We for our analysis we have adopted a connectivity pattern or a previous work that helps us generate a lot of kernels and applications for the Versal, that is charm. I'll give a brief overview of charm's connectivity pattern here. So charm basically uses packet switching and circuit switching. These are two type of PLIO connection methods, which I'll discuss a bit in detail later when we go deep into it. But it basically is the way of connecting your AI engines. So you have your matrix A, which is first broadcasted and then packet switched to different AI engines, and similarly you have matrix B, which is kind of packet switched to different AI engines. The partial product that is generated after each AI engine is basically passed to the next AI engine using the cascade connection. So this is a very brief introduction of the framework that we have used for our analysis. Uh, Moving ahead, I'll show the outline of how our next presentation is set. So we talk about multiple research questions and we try to set up some experiments to answer them and get some results and try to generate some takeaways from the results. So we look at like the kernel programming models, size and shape, different size and shapes, and sensitivity to number of AIs, etc. So let's let's start with our first research question, which is what's the impact does kernel programming models have on performance? So AMD provides us with two programming models. One is intrinsics and the other is API. So intrinsics is a low level interface that they have provided, which gives you a very good control over the hardware. It's a bit difficult to write using intrinsics, and it is more close to the hardware, so you need to have a very good understanding of the hardware before you write your kernels in intrinsic. The other method is the API based method. So they have provided high level APIs for matrix multiplication, FIR, which directly can be used to write your application. So we try to write kernels in both these forms and see and check for efficiency. So a simple snippet of how an API looks is that you use an API called ML for matrix multiplication, and you provide the size. There are predefined sizes for MKNN and the data type. Similarly, you have an intrinsic which will do MAC operation. So it will just take two vectors and do a multiplication across the vector. So this is more of a low level in intrinsic, whereas API is very high level. So we used two sizes, 32 cross 32 cross 32 for FP32 and 64 64 64 for Int8, and obtained the result. So here we see kernel efficiency and the execution time. So kernel efficiency is the ratio of the actual execution cycles obtained from the AI simulator divided by the theoretical cycles. So the theoretical cycles are calculated using the number of max that are required and divided by the peak throughput. So as we can see from the results that the intrinsic based kernels provide very high efficiency for both FP32 and Int8, whereas API based kernels are not that good for FP32, whereas they provide 5% less performance for Int8. We can also look at the execution time and the breakdown here. So on this graph where you see FP32 has almost intrinsic execution time of like 3.5 microseconds, whereas the API based execution is around 7 microseconds. In both of this, you can see that the compute and the read and the write are we have done a breakdown of read and write and compute, and we see that the read and write is same, which means that the APIs for the multiplication, the compute are basically causing the difference. The main takeaway from this analysis is that intrinsic based kernels are show high efficiency both for Int8 and FP32, and API based kernels have another advantage where they are very portable and portable to any Versal hardware. So if you change your Versal from say VCK5000 to VK280 or some other Versal hardware, you don't need to rewrite the entire kernels. You can just reuse them. So makes the design very much portable, but this is not achieved if you use intrinsic. You might have to change your kernels drastically. The other thing is that intrinsics is a bit difficult to design or write the kernel, requiring in-depth knowledge of the hardware. Moving to the second question, that is how does the workload size and shape affect kernel efficiency? So we took a bunch of workloads just to write a single kernel from say 2K max to 262K max. We use the intrinsics as it is more efficient. And this is the results that we got. So here we have kernel efficiency on the y-axis and different workload sizes for a single kernel on the x-axis. And we see for FP32, we get around 80% or higher efficiency for most of the kernels. We also get the breakdown of the read write and the compute time consumed by these kernels. And we see that most of the kernels here are compute bound and are not bound by your read and write time. So that's the main takeaways from this experiment. We do the same experiment again for Int8, where we again move the on the x-axis have different workload sizes. And here we can see a bit different trend where a lot of here the kernels or a lot of workloads have poor efficiency. Mainly greater than 80% efficiency is only achieved for workloads that are higher than 65K. We have debugged this to see that the AI engine has a setup time of some 40 cycles. And these workloads, which are very small, they have an execution time of say around 100 to 150 cycles, where this overhead setup overhead becomes a big overhead, and it basically brings down the efficiency. Whereas the large workloads do have the same overhead, but it doesn't show much degradation. Again, looking at the breakdown, we see that majority of the kernels here are read-write bound and not compute bound. So that those were the main takeaways from this experiment. Now we will look at how sensitive is performance to the number of AIs. So as we scale the same application to multiple AI engines, how does it scale? So we use for this experiment, we use one big matrix of say 4K cross 4K cross 4K. We use Chom's design pattern, and then we on the x-axis we vary the number of AI engines from say 16 to 384 for FP32 and similarly for Intel. We see that the performance scales pretty well. As we go to 384 engines, we don't see much degradation. The takeaway is that for this particular size, which is a square matrix, we see very good performance scaling. So we also try to see the same scaling for, say, asymmetric matrix, because most of the real world neural networks have asymmetric matrix sizes. Uh, the results are not as expected, because we see that some of the for example, the workload where the k dimension is very small, we see that for FP32 and configuration with 256 AI engine is performing better compared to one with 384. So here using more engines is not pretty helpful, and this is seen for most of the other cases where we have a bigger k dimension and a smaller M and N dimension. We see, for example, here 128 shows better performance compared to 256 and 384, and this is majorly because of the padding. So due to the way these computations are set up for say 384, there is a specific minimum compute size, and that compute size is used as a way to factor the bigger size of metrics. And it results, if it results into padding, then it basically brings down the performance. So highly asymmetric workloads, as we see, do not scale just by increasing the AI. We have to maybe tweak a lot of other things, and padding plays a very important role here, and which is needed to be considered when you design the actual hard workload or the design AI design. So before moving ahead, I would like to give a brief overview of this. So analytical model. So we have developed an analytical model for the same for the same design pattern that can give us say performance estimates if we provide how many engines we are going to use, how much of the BRAM we are going to use, and what tiling dimensions are we selecting. So this analytical model that we produced give us an accuracy of say plus minus 5% with the actual compared to the actual hardware runtime, and this also provides us with say detailed breakdown of various execution artifacts, like how much time is consumed by a specific say DDR or the AI. So we get this information from this analytical model. So first thing we get is the analytical model time, that is the complete execution time. We get some AI cycles. So these cycles are basically consumed by either the compute or the PLIO data transfer. We also divide this AI cycles into specifically compute cycles and specifically PL AI non-overlapping data transfer. So most of the design that we used has double buffering in both the stages, where at the AI engine and also at the PL interface. So most of the data transfer and the compute is overlapped, but there is some warm up required, which is contributed or which comes out as the non-overlapping data transfer. Then we also have the time that is consumed by the DDR. So now we can see we have an example here that runs an 16 AI configuration, which shows around different breakdowns here. So we have say 10 have around 100 milliseconds of time consumed by the DDR, which is overlapped with the AI cycles, and then we also see how much time is the actual compute and how much is the non-overlapping data transfer. So this gives us a good picture and gives us an insight on what needs to be done in order to accelerate this particular example. And we also have the hardware execution time here to show that it's very much close to the analytical model. So again, coming back to the research question of the performance to the number of AIs. So we see use the same workload here, and we basically plot the breakdown for all the different configurations we have. And this basically tells us that as you increase the number of AI engines, the thing that basically bounds your performance changes. So for 16 AI engine, it was the AI cycle, the total AI cycles. But as you move towards say 256 AI engine, you are also blocked by a DDR. So that's the main takeaway from this breakdown analysis, that some of the configurations earlier are constrained by cycles, AI cycles, whereas some are constrained later are by DRAM bandwidth. So now before moving to the next analysis, I'd like to give a brief on packet switching and circuit switching, as they play an important role in the next experiment. So AMD provides a method to reuse the PLIO. That is, you can do packet switching where you can communicate a single data packet that to one AI engine, and at t is equal to another data packet to another AI engine through the same PLI. So you ideally you would have used two different PLIs to communicate to two different AI engines, but here you save the PLIO and just reuse it. So here, like for t is equal to 0, you communicate to this AI engine, t is equal to 2, you communicate to this AI engine. So advantage is, again, you say reuse the PLIO. The disadvantage is it kind of serializes the operation. The other way to reuse PLIO is called circuit switching, where you if you have the same data, you can transfer it to all multiple AI engines at the same time. So this also helps in reusing the PLIOs, but at the same time, this is only applicable where you have a broadcast kind of an application. So now we see how sensitive is the performance to say the number of PLIOs. So we use 16 AI engine configuration and try to vary the PLI usage from 3 to 36 for the 16 AI configuration, and use the same workload, say 32 cross 128 to see the effect on performance. So the first experiment is with just 3 PLIOs, so very conservative. Every AI engine is connected using the same PLIOs. And if you look at the result, this takes around say 18 microseconds of total time to run this. Yeah, now we improve the design a bit and say add more PLIOs. We use 7 PLIOs here, and these 7 PLIOs communicate data using circuit switching and packet switching to the AI engines. And here we see a drastic, like 3.3x improvement in performance. Similarly, if you want to do an extreme design and use as much PLIOs as you want, you can attach one PLIO or two PLIO to each AI engine. And that way you will see very good performance, but this also costs a lot of resources. We also have some middle points here where we tried 4, 6, and 33. So the main takeaway from this is that uh, sharing PLIO resources is helps us save resources, but also costs some performance. So we should always look at some moderate PLI usage where we still get good enough performance near to the max, and we can save a lot of PLIOs. Like for example, here is this 7 PLIO configuration. Okay, moving ahead, we also talk about we also profile different schemes which used for communicating between AI engines. So there are three different ways to communicate data from AI to AI. We name it in this fashion. So one is wire switch connections, the other is using the cascade connections, and the other is using a buffer. So the cascade connection is a hardware provided, a bus direct provided in the Versal. So it's only used to communicate between near neighbor AI engines on the same row and only in one direction. So the AI engines on this row will only communicate, say, from left to right, and on the alternate row from right to left. So this is a streaming interface, and it's only in one direction. So the other is wire switch connections, which helps us communicate from any AI engine to any AI engine using the switch network. It's also a streaming kind of an interface. Then we have the buffer interface, which helps us communicate from, say, one AI engine to the neighboring AI engines. Since they share memory, we can just create a buffer in the memory, and it can be written in it. I'll go over each of them in a bit detail with some performance. So we use Cascade for first, so which has around 384 bit width interface, and it basically communicates in only one direction, and that is we consider as the baseline for our comparison with the other interfaces. So Cascade is just a baseline here. Moving to buffer interfaces, so we have near, so the AI engines in near, which are near to each other, share their memories, and the memory interface is around, it's 256 bit. So whenever we need to write some data, or we need to communicate data from one engine to the neighbor, we basically write data into its memory, and that same memory is again read by the other engine. So this when is only applicable for near neighbors, and also it comes with it's a bit slower, 50% slower than Cascade. This is majorly because the producer needs to write the data completely into the buffer before the consumer can read it, and this kind of locks the application until the producer has finished writing the data. Then we have the wire switch connection. So here we have a 32-bit connection from, say, any engine to any engine using the switches. This 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 is this communication scheme can help us communicate far away engines. And to our surprise, it's not much. It only takes like 3% performance it compared to Cascade. So the main takeaway from this is, wherever possible, we should use the cascade communication method, as it is fastest of the three. Uh, yeah, so let's look at some real world workloads, which basically we see if they are, how do they fit in the Versal, or how are they bounded by? Are they memory bound or the compute bound? So we use some real world networks like BERT, VIT, Llama, and get some sizes of the matrix that are used in these networks. And we try to draw a roof line where we try to plot these networks on the roof line. So on the right, you can see a roof line with two slopes. One is for DRAM, the other is for the PL, and we have different roofs for, say, max AI engine. Say if you use 400 AI engines, or this is the max compute performance stops, and there are different configurations. So here we can see that workloads like Llama 270 billion, which is very huge metric sizes, is on the left side of the ridge, which shows that these workloads are going to be memory bound, whereas all the other workloads here seen, they are mostly compute bound. So the thing we seen is here, this red circles here indicate that we don't consider the effect of tiling. Since we use the PL memory as a local memory for most of our experiments, we have to do a lot of tiling, which basically increases the pressure on DDR. So just taking, if we consider tiling into the consideration for plotting workloads, we see that majority of the workloads, majority of the networks here move from being compute bound to memory bound. So the green circles here are the workloads with considering the tiling effect. So the main takeaway is that tiling overhead moves majority of the workloads here to being memory bound, and most of the part we never use the bandwidth of the PL to AI, which is very high bandwidth for a matrix multiplication kind of workloads, because most of the time we are bound by the DRAM. Yeah, that's all. Thank you everyone for listening to this presentation.